All these scenes have one thing in common. Some object, large or small, moves through a gas or a liquid. In each case, the object experiences a resistance to its motion through the fluid. This resisting force is called drag. Unless some other force is applied to overcome the drag, the object will decelerate. Fluid dynamics is concerned with gases and liquids in motion, in particular with the forces applied to objects by liquids and gases in motion, and conversely with the way in which these fluids move under the action of forces applied by objects. Before Galileo performed his famous experiments at the Leaning Tower of Pisa, it was thought that a feather falls more slowly than a steel ball because it weighs less. Now we know that the feather falls more slowly because, as compared with their weights, the air resistance for the feather is much greater than for the steel ball. We can prove this by allowing the feather and the ball to fall simultaneously in this tube from which the air has been evacuated. Here at the top of the tube, ready to drop, are a steel ball and a feather arranged to be held up by a strong magnet. There, the feather did fall just as quickly as the steel ball. As a matter of fact, the speed of fall in a vacuum is the same for all bodies, regardless of their size, or their shape, or their material, or their weight. When we removed the air resistance, both the feather and the ball fell freely with the acceleration of gravity. If only the Greeks had been able to perform this experiment, the principles of mechanics might have been discovered 1,500 years earlier. What the Greeks thought, you remember, was that to keep a body in motion with a constant velocity, it is necessary to push on it continuously with a force, while Newton taught us that if a body is to move with constant velocity, the net force acting on it must be zero. The Greeks made their experiments on flying stones, arrows, and the like, but they did not understand that the air, although invisible and impalpable, exerts a resisting force, which slows the object unless some additional external force is applied to overcome the drag. Over the past century, tremendous strides have been made in our understanding of the fluid mechanics of drag. Now I would like to show you, in the laboratory containing our demonstration wind tunnel, some curious phenomena relating to drag. We have here a small open-jet wind tunnel. The air escapes from the settling chamber through this nozzle at speeds up to about 230 miles per hour and may be controlled. You can see that this jet is something we can really work with. For instance, we can suspend models in the jet at this end of the lever arm system. The lever arm is mounted in ball bearings which act as a fulcrum point. The drag force exerted on the model by the airflow is transmitted through the lever arm to this spring weighing scale on which we may measure the force. These weights are counterbalance weights which we can mount to counterbalance the weight of the model so that the scale will read zero when there is no airflow. The can here contains a viscous oil to damp out oscillations in the pointer reading which arise due to any instabilities in the airflow. During the experiments, we would like to measure the airspeed as well as the drag. The airspeed is determined by the pressure in the settling chamber from which the air is supplied to the nozzle. The pressure is led by this tube to the pressure measuring instrument. The liquid level in the tube gives us the airspeed directly in miles per hour. Now I would like to begin with a few experiments with a specific object in mind. That is, I would like you to realize from the outset that sometimes what happens in a fluid flow is not what we may expect. This will suggest to us that many phenomena in fluid mechanics are very complicated indeed, and it will caution us to be on guard against reaching oversimple conclusions. In the first experiment, I suspend a 3-inch sphere at the end of the lever arm in the air jet. We are going to increase the airspeed and see what happens to the drag force. I'm going to start the motor now. Here we go. You see that we have brought the speed up to about 75 miles per hour, while the drag force reads about 1.5 units on the scale. I'm now going to increase the wind speed to about 100 miles per hour. The wind speed, you see, is about 100 miles per hour, while the drag force has increased to something a little less than 2.5 units. Now I am going to increase the wind speed continuously, and I'd like you to observe what happens to the force on the scale. Here we go. Up, 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 but now it's going down, down, and up again, up, up. She's continuing to rise, continuing to rise. Now that was very puzzling, and it's not quite clear what happened, so I think we'd better repeat it. I'm going to reduce the speed to about 75 miles per hour again, so that we can do this all over again and make sure that we saw exactly what happened. There we are, back at about 75 miles per hour again. Now I'll remind you that the puzzling thing that happened occurred when the force on the scale reached about 3 units and then suddenly dropped back to a little less than 2.5 units, after which it began to rise again. All this while the speed continuously increasing. I'll keep this button pushed all the time so that the speed continuously increases. Here we go. Up, up on the force scale, up, 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 down, 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 up again, up, 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 up. And now as she increases much more slowly in this second pattern of flow than in the first pattern of flow. Well, this is certainly unexpected. So as to make sure that we really understand what has happened, let us put our observations on the board in the form of a graph. On the vertical scale, we record the drag force. On the horizontal scale, the wind speed. As we increase the speed from 0, the drag force also increased, just as it does when you put your hand out of an accelerating automobile. But when the speed reached a certain value, we found that a further increase of speed caused the drag to decrease, but in a rather disorderly and oscillatory way, until we finally reached a speed at which the drag force once again increased as the speed increased, but on a different curve. We have 2 curves here in which the increase of drag with speed is quite orderly. And so there seem to be 2 distinct patterns of flow with a sudden jump or transition between the 2.